Hello everyone. In this video we'll be discussing combinations and permutations. And we actually discussed this a little bit in the last video. At least I mentioned some of these ideas in the last video. But here we'll be taking a look at it a little more detailed. I say first here, permutation is just a rearrangement of a set of objects. So for example, if you have A, B, and C, a given permutation would just be rearranging those in some way. So you have the same set, but there's just different permutations. So I'm going to write all the permutations of A, B, and C. So we have ABC, ACB, I guess BAC, BCA, CAB, and CBA. So in doing this, I don't know if we see it exactly, but I kind of give more or less a procedure of how to actually come up with all of these. Start up with your favorite first one, and then keep the first letter the same, rearrange the last two, and then kind of continue that idea. With 3, we see that that's really all I'm doing. So those are the only two involving this, or the first one is A. So then let's say the first letter is B, and then we have either AC or CA for the last one, and then here we have, for the first letter being C, we have AB and then BA. Now the actual number of certain permutations you get, basically just considering the slot method of counting, we have 3 different slots, 1 for each letter. We have 3 choices for the first letter, it's either A, B, or C. But there's no repeat here. You can't choose AAA, for example. That's not a permutation. Permutation is a rearrangement of ABC, right? There are no repeats. So with that being said, once you choose the first letter, you have one less letter to choose from. So for the second letter, we have 2 letters now to choose from because we already selected one for our first letter. Multiplied by one last possibility for this. So once you've chosen these 2, the last one has to be whatever other letters left. So notice when we multiply these, 3 times 2 times 1 ends up being 6, and there's a total of 6 different possible permutations here. Okay, so now we get into factorial, and factorial basically is the amount of ways you can permute a certain amount of objects on that entire set. Kind of like what we saw for this one. For example, if we look at permutation of 3 letters from a total of a set of 5 different letters, then it's a little different. So we're not using all of the 5, we're only using 3 of the 5. But here we're using all 3 of these 3 we had started with. So that would amount to a factorial. And notice that the pattern here is you just start with the amount you have, 3, multiply by its predecessor 2, multiply with the predecessor of that 1, and so on. So in fact, n factorial is defined to be this. N times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. So for example, 4 factorial would be 4 times 3 times 2 times 1, which of course is 12 times 2 times 1, which is 24. 3 factorial, for example, would be 3 times 2 times 1, which of course is 6. 2 factorial is 2. 1 factorial is 1. Just to name a few. I'm not going to write it, but 5 factorial ends up being 24 times 5, which is 120. There's a lot of nice patterns here. But the big one that always throws people off that I'm just going to get out of the way right now is that 0 factorial is defined to be 1. So this is more of a definition than anything. There is reasoning behind this. There's actually a few different ways to describe this. Basically, how many ways can you rearrange 0 objects? There's only one way to do it because you're not touching anything basically. So leaving it alone, I guess, would be the one way of doing that. Which I know sounds a little strange. Another explanation is that to get from 1 factorial to the next one, you multiply by the new face value. So if you go up here, scaling up, you would multiply by 2. From here to here, you would multiply by 3. From here to here, you multiply by 4. And I kind of mentioned earlier, to get the 5 factorial, you multiply this by 5, because you have 5 times 4 times 3 times 2 times 1. So on the other hand, to go backwards, you divide by the one you were at. So divide by 4, 24 divided by 4 is 6. Divide this by 3, 6 divided by 3 is 2. Divide this by 2, and then divide this by 1. You get 0 factorial is 1. So that's one way of kind of explaining why 0 factorial being 1 makes sense. It also kind of has to do with the fact that anything to the 0 power is 1. That's a little bit of a deeper connection, but it certainly is a connection. And now we get to this idea of k permutations of n elements. So we have n elements and we're permuting k of them. So like I said, kind of like this example, only let's say we had 5 things to choose from. So if you had, for example, A, B, C, and D, maybe I'll write it off to the side here. Let's say we're taking from the set A, B, C, D, and E, 5 elements, and we want to pick 3 of the 5. So if you pick 3 of the 5, our first letter could be A. Let me write it like this. So these are the permutations. We could have A, then B, then C, A, then, well, I guess then C, then B, A, then, there's a few others, right? Maybe this is another way of doing that. We'll do A, B, and A, B. Yeah. So A, B, C, A, B, D, A, B, E, and then switching those around. Trying to see if that's an okay way of writing that. Yeah, I guess we could do that. Switch those around so we get AC, or we could just look at AB, AC, AD, and so on. I think that idea works too. There's a bunch of different ways you can probably look at it. But let's look at AC. So we have ACB, ACD, and ACE, which is kind of like just swapping those around, basically, kind of. Well, I guess not really, because ACE wasn't here. But now what about AD? So we went from AB to AC to AD. We have ADB, ADC. Again, it kind of repeats, so we can't have ADA or ADD or anything like that. We can certainly have ADB. We can have ADC. We can have ADD, but we can have ADE. Notice that's a permutation of AED, which we haven't got to yet. And there's 3 of each of these, notice. So finally we have AE, so there's going to be 3 of those. And it makes sense because once you choose the first 2, for the third one you have a total of 3 left. Because choosing the first 2, you have 3 new ones left. So choosing AE means we have B, C, and D to play with for the last letter. So B, C, and D. If you want to count these, notice there's 5 of these like this. So it's a total of 5 times 5 times 5 times 5. Or I guess that was a bad way of saying it. There's 3 of each of these. I don't know why I said 5. There's 4 sets of 3, so it's 12 actually. So the way you'd write it is you would write 5p3, which is the permutation of 3 of 5 elements, basically. Now another way to write this, like an alternative notation, is p of n comma k. I like this though. This is more used in like a probability or statistics course as far as notation, but they're the same thing really. So, and also remember the slot method. That idea still works here. So there are 3 slots because we're picking 3 of these 5 elements. Okay. For our first element, we have 5 to choose from. We would have 4 to choose from for the last one. Notice, we definitely see that. Once we choose A to be the first one, we have a total of, and you know, I'm realizing now that this is not it, because these are the only ones, these are only the ones when A is in front. What about when B is in front, when C is in front, when D is in front, and when E is in front? Maybe that's why I meant to say 5. So if we do the same thing, but with B in front, C in front, D in front, and E in front, you'd have 5. So there's not 12, there's actually 12 times 5, which is a total of 60 in many ways. So that's interesting. But again, thinking of it with a slot method, it actually makes a little more sense. We have 5 to choose from for the first one. Here's A, for example. Once you choose the first one, you have 4 possibilities for the second one, B, C, D, and E. We see them here. And then for each of those, you have 3 to choose from for the last one. So for example, here, we have 3 different possibilities for the last one once the first 2 are established. And notice 5 times 4 is 20, times 3 is definitely 60. So it's kind of interesting to see that. But from this formulation, it ends up being n factorial over n minus k factorial, which basically is the slot method. So, and it's not obvious why this expands to this, but if you actually wrote it out, maybe I'll show that here. Kind of alternatively, 5pk is 5 factorial over, or 5p3 I meant to say, alternatively, is 5 factorial over 5 minus 3 factorial. Now, 5 minus 3 factorial is 2 factorial in this example. 5 factorial is 5 times 3 times 2 times 5 times 4 times 3 times 2 times 1. There we go. And 2 factorial is just 2 times 1. So in fact, the second way I have writing this formula takes into account the cancellation that occurs in this fraction. There will always be cancellation because remember, every factorial contains the previous factorial, or contains a previous factorial. N minus k is a smaller factorial than n factorial, so is thus contained in that, so there's cancellation there. Okay, so that's kind of all I wanted to say about permutations. Maybe we'll take a look at another example, but I think that's really it. We'll actually see more of this when we discuss combinations right now. Okay, so here finally we have combinations. And I say combination is just a number of ways to select k of n objects without considering permutations of this selection. So for example, when we saw A, B, C, that would be one selection. B, C, A would be the same selection because you're still selecting A, B, and C. So the ordering doesn't matter here. We're not counting those. And in fact, as we will find out, we'll see this right now, this is just NCK, n choose k, which is what we've seen before, binomial coefficients from the last video. But actually what this really is, though, is npk divided by k factorial. We'll see that in this example a little bit. But basically what we're doing is we are selecting k of n objects, but then taking away the total permutations, which you'll have k factorial permutations for a given selection. So like ABC had a total of 6 different permutations. There was BCA, BAC, and so on. We saw those at the very beginning of the video here. And dividing by k factorial removes all of those, so you'll have a total number of just your selection without the permutations of those selections. Since npk from the previous board was n factorial over n minus k factorial, dividing that by k factorial just basically allows us to multiply k factorial to the denominator of this. And after kind of considering cancellation, we get this formula, which I showed at the end of the last video, actually. Okay, so here I have an example. How many ways can 3 or 4 people be selected for a certain project? So let's say you have 4 people working in an office or something, and you're the manager or whatever, and you want to pick 3 of those people and task those people to do a project, while the other person that you're not selecting does some other assignment or something like that. So how many different ways can you choose 3 of those 4 people? Well, notice there is no given like task for each one. So when you have a question stated like this, where it's very like vague, choosing 3 of 4 or choosing 3 of 7 or 5 of 7 or whatever of whatever, if there's no assignment of these things, then you're just doing choose. So here, this would just be 4 choose 3, which according to the formula is 4 factorial over 3 factorial over the difference factorial. Now 4 factorial, of course, is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. And 4 minus 3 is 1 factorial, which is just 1. So we see that all these cancel, and we just get a total of 4 different ways to make this selection. And in fact, what's kind of interesting is the way I actually phrased this question at the beginning. Well, maybe not phrase it, but the way I kind of thought through it and kind of gave that example where you're selecting 3 or 4 people. But I also said that what happens with the person you did not select? They would just be doing something else, right? So one way to phrase this is that how do you select that one person that's not on the project? So 1 of 4 people could stay, so there's 4 ways to select that one person. So if you select that one person to stay, everyone else goes in the project. So that's another way, another valid way of saying that. In fact, that's just noticing that 4 choose 3 is the same as 4 choose 1, which we know from Pascal's triangle with that whole symmetry we saw. But again, that's something to kind of consider. In fact, Pascal's triangle is another way we could have actually arrived at this conclusion. We can create Pascal's triangle all the way up to the 4th layer, which is right here, and see that 4 choose 3, 0, 1, 2, 3, this is our answer. But I was saying that earlier, just now, in fact, this is the same as 4 choose 1. So it's a different way of thinking about it, but it certainly holds. Now, I want to also say that, if you task these people with certain assignments, let's say one person is the photographer, the other person is the interviewer, and the other person is the, boom mic or something like that. or maybe just like the director of the whole interview or whole project, whatever you're doing, right? It doesn't matter. The whole point is you're assigning them, but they are each tasked with something. That's really a slot method problem because now you are tasked at basically assigning each person to a specific assignment. So choosing 3 of 4 people, so an entirely different question, but choosing 3 of 4 people, you can choose 4 for the first task, for a first assignment in that project, 3, once you've chosen that fourth one, the one for the first person of those 4, then 2 for the last assignment. So 4 times 3 times 2 ends up being 24, right? So, but that is actually, really this is just for P3, not for C3. So what is the difference? Well, what I'm going to do is I'm actually going to label these people as A, B, C, D, like we have in the past, and we're actually going to write them out, and I'll show you exactly what's going on, and it explains why this is true. It won't take very long either. Maybe the largest part of this would just be selecting. So let's say we're selecting from the set of people, person A, person B, person C, and person D. Let's say those are like their first names or something. Like Al, Bob, Carol, and Dan, or something like that. So we have ABC, ACB, well, you know what, I like the way we did it before where we have like ABs and ACs and so on. Let's do it like that. So starting with A, we have ABC, ABD, and then AC, we have ACB and ACD. Okay. And then we have AD, so that's ADB and then ADC. So these are the amount of possibilities when you pick A first, okay? What about when you pick B first? So we have B, you kind of see what happens, right? You have 6 possibilities here. We have BAA, BC, BD. We have C then D, and we have A then D, and we have A then C. If C is first, you have 6 possibilities here. Let's see, A, then B, then D, B and D, A and D, A and B. Okay. It's a little weird, but it definitely makes sense. So when D is first, we have 6 possibilities again. D, 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 and D. Okay, A, B, B, C, C. So we have B and C, we have A and C, and we have A and D. Perfect. So if you're tasking them with assignments, then these are the total 24 different possibilities. Notice 4 times 6 possibilities. But notice, if you don't care about the permutations, you're actually taking away 6 of these. So what's not obvious here is that the ABCs, there's 3 of them, okay? Where are my other ABCs? I guess here, here, and here. So that right there are 6 of those that would correspond to the same if you're not giving those people assignments. And you can see, for example, that so is ABC, but what about like another selection that's not a repeat? So let me circle it in blue. I don't have enough colors to circle all of these. Maybe I actually do. So ABD, that's an ABD, that's an ABD, that's an ABD. We have 2 more. So let's see, that is an ABD here, and this is also an ABD. So now let me use green. So now we have CAD, which is the same as this one. Anything with a C, an A, and a D are going to be circled in green. An A, a C, and a D, right? So notice we have how many circled in green so far? That's 5, and then I guess, oh no, I'm sorry, that's not 5. That's a total of 6. Perfect. And now I'll circle in black, and notice there's just 6 of them left. So what I've circled in red, what I've circled in blue, what I've circled in green, and what I've circled in black are the 4 different ways to select them without assignments. Because the reds, for example, ABC, BAC, CAB, they're all the same selection. That's not considering, or I guess ignoring, the permutations of that given selection. something to think about, but that definitely explains it and sums it up, I think, in a very nice way. Now that concludes our discussion here on combinations and permutations. So thank you all for sticking through and watching this, and hopefully the explanation of things made sense. I think it was pretty clear, but I hope you feel the same way. So thank you all for watching, like I said, and I will see you in the next video.